Our title today is Graham's Law of Effusion. It's not my law, but it still has my name. So, Graham's Law of Effusion So, let's begin with the scenario. You're having a big party, and you are going to get all kinds of helium balloons because you want your whole living room ceiling to be covered with helium balloons for this party. And you think, I'd really like to be prepared for this party. Perhaps I should go buy my helium balloons the day before the party. And I ask you, would that be a very good idea? If this was you and you were the party planner, would you buy the balloons the day before? Would you buy them the day of the party? I think we all know the answer to that question. If you bought them the day before the party, and you woke up the next morning, where would you find the balloons? On the floor. So why is that? Why is it that the helium balloons sink overnight? This is why. Okay, so first of all, let's talk about diffusion versus effusion. I'm going to do some really sad drawings here. Okay, so we've got an Erlenmeyer flask. Well, and it's kind of lopsided. And let's say it's filled with some kind of stinky gas. Let's see, hydrogen sulfide gas. Okay, and notice, you guys, it's got a cork in it. It has a cork in it. Now, what is going to happen when we lift this cork off of this flask? Well, this gas is going to escape. It's going to diffuse, meaning it's going to go everywhere. Okay, so diffusion is simply the movement of fluid molecules. Get out of here, Cliff. Opportunist. Okay, so diffusion is the movement of fluid particles, so either liquid or gas, from an area of high concentration to low concentration. And it's a completely random process, and so gases diffuse all the time. And we know that. Sometimes it's embarrassing, right? We want to keep our gases to ourselves, but it never stays that way, right? They diffuse. They go everywhere. They will take up as much room as you give them once you open up that container. Okay, effusion, on the other hand, effusion is something very, very different. Okay, so this should be in 3 dimensions. It's not going to be in 3 dimensions. So let's say I've got a chamber, and in between this chamber, okay, I've got this little tiny, and you're not even going to be able to see it. It is so dinky. I've got this little dinky hole between this chamber and this chamber, and this one's all filled with gas. Okay, and they're moving, and every so often what's going to happen is one of these particles of gas, right, they're hitting against all this other side of this barrier, But every so often, one of those molecules is going to actually get lucky and just go straight through the hole, and there we've got one molecule over on this side. And then more, and oh, lucky, and there it is, the molecule over on this side. So, by definition, you guys, effusion is defined as a gas passing through a tiny pore. Okay, so effusion means that the gas particle actually is just getting lucky, and it's going through a very tiny microscopic opening here, and that's just completely random. Okay, so diffusion is everywhere. Effusion is just a single molecule passing through a little tiny pore or opening in a surface and escaping or moving to another place. And this is what happens with the helium balloons, is that, you know, the helium just, the molecules just get lucky, and there's little microscopic pores in the balloon. And eventually, bumping up against the side of that balloon enough, they're going to find the opening and they're going to go out. All right, so that's effusion. Now, what is Graham's law state? Graham's law says that the rate of effusion of a gas is inversely proportional to the square root of its particles. Right? That's perfectly clear, isn't it? You don't need any explanation for that. Okay. So there's got to be a formula associated with this, right? So let's write the formula that is generally associated with Graham's law of diffusion. And that is going to be R1 over R2 is equal to the square root of the molar mass of 2 over the molar mass of 1. Okay, so generally, you guys, we use Graham's law to compare effusion rates of two different gases. All right, that's where we see where we see this thing used the most. Is comparisons between two different gases. Okay, so for instance, calculate the ratio of effusion rates. Calculate the ratio of effusion rates of hydrogen gas, which is H2, and uranium hexafluoride. UF6. Okay, so I'm going to do it up here, you guys, in that space right there. Okay, so what we're going to do is we are going to say that the rate of H2 over the rate of UF6, rate 1 over rate 2, is equal to, and this is where people make their biggest mistake, you guys. Okay, notice the molar mass of 1 goes in the denominator, right? They are inversely proportional. Inversely proportional. So that means that I am going to say, what is my molar mass of hydrogen? 2.02 grams per mole. What is the molar mass of uranium hexafluoride? It's a monster. Very, very large. 352.02. Okay, so I'm going to do this division, and then I'm going to take the square root of it. Okay, I'm not going to take the square root of each and then divide. I'm going to do the division, and then I'm going to take the square root. And what that will give me, you guys, is a number that is 13.2. Okay, so what does that mean? Well, 13.2 isn't a ratio. What is a ratio? 13.2 to 1. And so what is that saying? It's telling me that the hydrogen effuses 13.2 times as fast as UF6. Okay, that's what that ratio is telling me, 13.2 to 1. That for every 13.2 hydrogens that pop through that little tiny opening, 1 uranium hexafluoride will do that. Or for every 1 uranium hexafluoride that pops through that little pore or opening, 13.2 hydrogens will go through at the same, in the same given amount of time. Okay, let's do another problem. 4.5 minutes for 1.0 liters of helium to effuse through a porous membrane. How long will it take for 1 liter of chlorine gas? Okay, it's another way we can see the problem. And we'll see yet another way that they can ask questions tomorrow in class about this. All right, so it took 4.5 minutes for 1 liter of helium to effuse through a porous membrane. How long will it take for 1 liter of chlorine? So what we want to do, you guys, is we want to compare these two effusion rates. And so again, we are going to say the rate of helium over the rate of chlorine is equal to the square root. And what am I going to put in the numerator? I'm going to put the molar mass of the chlorine, which is 70.9 say 70.9 divided by 4.0, and then I'm going to take the square root of that, and that is going to give me a number that is 4.21. Okay, so what that means then, if I want to make it into a ratio, is that for every 1 chlorine, I've got 4.21 heliums, or 4.21 heliums for every 1 chlorine, or that helium effuses 4.21 times. Yeah, that's really the way I should say it. 4.21 times faster. That's definitely the way I should be saying it. See the problem when we're teaching these things one time during the day. All right, so what that means, you guys, is 4.21 times as fast. And I guess that's what I wrote over on the other side. And so how do we solve this problem then? Well, we say if it took 4.5 minutes for the helium to effuse, and it's effusing 4.21 times faster, we're just going to simply multiply it, right? And we will end up with an answer of, oh look, I don't have that worked out on my paper. So you guys do that multiplication, and I will look for it in your notes tomorrow. And that's it for my law.